So here's a matrix, I'm calling it P. I just want to do one more example of finding a basis for the row space and the rank, and the basis for the null space and the nullity. So I am not going to do this. Now this guy reduces to, so I've done the row reduction ahead of time. On the side it reduces to 1, 0, negative 3, 0, 0, 1, 0, 2, 0, 0, 0, 0. So once we have our matrix row reduced, we can read the basis for the row space. So remember, the row space is the vector space that is spanned by the rows of this matrix. So row reduction checks for independence. If you end up with a zero row, you had some dependence in here, which we did. So these two rows are independent if it's row reduced. So we have the two vectors that make up the basis for the row space are these two. And so the row space has dimension 2, so that means the rank, which by definition is the dimension of the row space, is equal to 2. So now let's look at the null space. I'm going to take the row reduced matrix 1, 0, negative 3, 0, 0, 1, 0, 2, 0, 0, 0, 0. So the null space is all the vectors that get sent to the 0 vector. This is also called the kernel of a matrix, by the way, I think. So this is a 3 by 4 matrix. So we're going to need a 4-dimensional vector, x, y, z, w. So some subset of things that look like this, where x, y, z, and w are real numbers, this is 4 by 1, are going to get sent to the 0 vector, which has to be a 3 by 1 in this case, in order for everything to work out. So we know the rank is 2, the number of columns is 4, so I know the nullity has to be 2 here. So that's a good check on your work. So we end up with the system, if you do this row by column multiplication, you get x minus 3z is equal to 0, and y plus 2w is equal to 0, and z, it can be anything. Let me say that's free, and w is also free. So from this, I can solve for x in terms of z. I can solve for y in terms of w. Z is free, so I'm going to call that s, and w is free, so I'm going to call that t, which means that I have my vectors x, y, z, and w look like x is going to be 3z, z is equal to s, so you have 3s. Y is going to be negative 2 times w, which is t. Z I've called s, and w I've called t. And you don't have to translate over to these parameters if you don't want to. You can work just in terms of x, y, and z, because they're going to disappear anyway. So what I'm going to do is I'm going to take this vector, x, y, z, w, and I'm going to split it into two vectors, an s vector and a t vector. So I have s in the first component, no s in the second component, an s in the third component, and no s in the fourth component. And then I'm going to add that to my t vector. So I have no t's in the first component, I have a negative 2t in the second component, no t's in the third component, and 1t in the fourth component. And then I can factor the s out of here and the t out of here. So a vector, this vector x, y, z, and w, if it's going to be in the null space, it's going to have to be a linear combination of these two things. So these two things form a basis for the null space. And there are two elements in it, of course, because we knew it had to be 2 because of the relationship among the rank, the number of columns, and the nullity. So I lost track of my thought there. 0 and 0, negative 2, 0, 1. So the null space, there's a basis for the null space. It has 2 components, which means the dimension of the null space is 2, and by definition, the dimension of the null space is called the nullity, is equal to 2. And again, we have the rank plus the nullity is equal to the number of columns there, which is 4. So there's one more example of row space and null space for a matrix. Okay, very good.